So now I turn to Dominique Bajeux, who is physically in this plateau, so it's why I'm looking at him. So Dominique comes from space systems, and when we ask to experts from space system and having rubbed shoulders with hydrogen, I face two types of reaction. Some people answer, "Oh, hydrogen is mastered. It's just a question of transposition to airplanes. In 10 years, it can fly. It can be operated." And some others say, "Oh, you don't figure out the difficulties with hydrogen." So I'd like to know what is your position with respect to hydrogen transposed to airplanes when considering that the difficulties that you know very well has to be transposed in an aircraft with passengers with probably a different level of safety to be which is required, aircraft which fly more than 10 hours per day and with routine operations. So what is your position?
Je ne vais pas vous parler de technologie.
Well, I'm not going to tell you about new technologies or new research, or indeed adapting technologies from rocket technology to aircraft. But there are adjustments needed to create liquid hydrogen. We didn't decide to use this type of ergo for environmental reasons. It's simply for reasons of energy efficiency. So liquid hydrogen is what makes it possible to have the fastest thrust on an engine. And when you can take it on board, when you can use it, you do use it. And that was decided a long time ago on the Ariane system. On the American side, it's the same thing. And so liquid hydrogen is a choice of energy efficiency that makes it possible to improve the onboard efficiency of mass, make sure that the whole thing doesn't fall back to Earth. So once the decision was made on these grounds, well, then you have to do with, or make do with the physical constants that it comes with. So you have a low density. So you need a volume to have a fuel tank full of liquid hydrogen. And for the Ariane rocket, well, the idea was to have a certain size on board, and quickly you're looking at a 5-meter diameter, and then how can you take that hydrogen on board? At 2/3 of the rocket is dedicated to accommodate the liquid hydrogen. The first stage is 30 meters, is just one big tank. And so the geometry of the whole thing is very much determined by the ability to take hydrogen and the volume needed to deliver the performance. Now, there's one thing that aircraft don't have. These rockets, well, don't have liquid hydrogen. What you have is oxygen instead. Oxygen is heavier but doesn't take as much space, and so you have a 5-to-6 ratio between hydrogen and oxygen, and then you put the oxygen where you can in such a way as not to take up still more space. And so the density is the first issue. How to design the aircraft, or the spacecraft rather. And one, you transport hydrogen well through the valves. I mean, if you have a plane flying for 10 hours, you want that the dynamic abilities of the aircraft to be still valid 10 years down. Well, for a rocket, you only have 1 hour, but you want to have 23 degrees Kelvin has to be remain the same temperature after 1 hour for the ergol, and it takes almost nothing to change the temperature. If the slightest circumstances might bring about a change in temperature, and that might destroy the engine. And so, I mean, your spacecraft can land, but then the engine can be irreversibly damaged. So it's not just the ability to transport that fuel, that ergol, but to make sure it remains in the same state. And then filling up, how much ergol can you take on board? And that, well, the amount you have determines the mission. I mean, it's a shame to take on board unnecessary liquid hydrogen. So the right balance must be struck. The engine, liquid hydrogen, oxygen as well, and that will determine the mission. That is what you can do, and the weight of the satellites must be reached. When, I mean, you have to work out how can you complete the mission having exhausted all the hydrogen. But if all the hydrogen is exhausted, then the engine will explode, and that's one of the problems. You can't afford to run out or to switch off the engine because there's no more hydrogen. So you're talking here about minute level of hydrogen, liquid hydrogen, that are kept in such a way as to be able to stop the engine before you run out.
The problem being, quite simply, that, you know, this is a living environment where there can be shocks, considerable thermal exchange with the inside and between inside elements also. And the liquid tends to become a gas, and you end up with a two-phase mixture of liquid and gas, and you have to find the right level so that you can provide guarantee propulsion. And so there are a number of measures that have to be taken to provide for stability. Again, you could take the example of a plane that has to fly for 10 hours and then land in New York. You have to make sure that you have the right amount of ergol and have the right amount of residual ergol. It's the temperature problem. Another difficulty that we encountered and resolved for the Ariane system is a very straightforward one of air tightness. Liquid hydrogen quite naturally turns into gas, and as compared with other gases, it has a specificity, which is that it can infiltrate anywhere. So an engine could be airtight for nitrogen, but won't necessarily be for hydrogen, so that being able to fully master this recurrent issue of enabling the flows of liquid hydrogen not to escape is very important. You learn different kinds of technology for soldering, for fitting the lines in such a way that you can reach production levels. We could ask, for example, an industrialist in Europe to build some kind of seal, perhaps, that would be able to work with liquid hydrogen, but they will be able to work with equivalent materials with other kinds of gases to check that this is fully airtight system. But when we test it in real conditions, it may turn out that it isn't. Another problem with liquid hydrogen has to do with pollution. If you have a fluid circuit and a reservoir like that of Ariane, when you fill it up, of course, you have to clean it first and remove any impurities with relatively classic methods. So before you fill it, you have to remove all of these gases that have the unpleasant habit of solidifying when the hydrogen comes in, particularly water vapor, which is a true catastrophe for liquid hydrogen. You have to remove it. If there's the slightest trace of humidity, this will lead to the formation of these small structures, a little bit like frost, and wherever there is an L-shaped pipe or an entry point, the system will effectively be clogged up. To get rid of this water, you have to make sure before you fill that you carry out sweeping, as we call it, using nitrogen, first of all, to remove the humidity, and then finishing up with helium. The problem being that with liquid hydrogen on a launcher, it takes a lot of helium simply to clean up these circuits. And a final point, which is useful to bear in mind, is that all of these different processes, the weight mastering, the temperature, and the airtightness, you have all of these problems on the ground as well. You have to provide for separation, and it's complicated. And so there are all these constraints also on the ground when it comes to also to the security and the access of the staff that has to do with
so you list
temperature
a
and
lot of
pollution.
problems, but I think you believe that they can be solved by technology, by research and development.
I believe so, indeed. The technologies that were used for Ariane, for space development, could be used in other contexts. We should never forget the life cycle aspect. I was talking, about the difference between planes and launchers. Launchers are one-time uses normally. And another problem is that in terms of production, you need to make sure that any technology you roll out can be easily checked and implemented so that it's actually feasible over a period of years. And this means that there are all kinds of technologies that exist and which are mature, but you have to make sure that you make the right decisions in terms of operational use.
So